Welcome to our video presentation on GelFusion. Popular end-to-end imitation learning policies for robotic manipulation, such as diffusion policy, heavily rely on visual features for understanding the state. However, this approach faces a significant bottleneck in contact-rich scenarios where visual input is often compromised. More specifically, an example is the scene degradation that occurs when trying to erase a whiteboard, making depth difficult to estimate. Occlusion frequently occurs in operations involving assembly or tool use, often when the gripped object blocks the details required for critical steps. To overcome the limitations of visual information in contact-rich scenarios, GelFusion incorporates a powerful tactile sensing technology. GelSight, a classic high-resolution Visuotactile sensor, captures membrane deformation with an internal camera to encode tactile information, provides rich contact information detailing surface properties and interaction dynamics. Despite this potential, effectively fusing visual and visuotactile modalities for robust policy learning remains a significant challenge, risking information loss or dominance by one modality if not carefully designed. To address the fusion challenge, we introduced GelFusion, a vision-led framework that integrates visuotactile feedback and vision inputs for policy learning, employing a cross-attention mechanism for vision-dominant cross-modal fusion. To sufficiently extract useful features from visuotactile images, GelFusion proposed a dual-channel visuotactile feature representation. High-dimensional spatial features are extracted via a ResNet backbone applied to each individual tactile frame. The features capture fine-grained details about the object's surface texture and the precise geometry. Low-dimensional dynamic features are derived from calculating differences between consecutive tactile frames, specifically encoding crucial temporal interaction events such as contact initiation or cessation. We provide extensive empirical validation across diverse contact-rich tasks, including surface wiping, precise peg insertion, and fragile object pick. For surface wiping, vision-only policies often struggle with depth ambiguity, resulting in inconsistent contact. For example, the policy may underestimate the distance from desk surface to wiping air without making proper contact. Conversely, overestimate the distance or fail to detect contact, causing it to apply excessive force and potentially damage the GelSight. GelFusion, leveraging its tactile feedback, consistently maintains appropriate contact and pressure, achieving effective surface cleaning across varied scenarios, including surfaces with different shapes and varying line positions. For precise peg insertion, visual occlusion is a major hurdle, especially during the final alignment. While vision-only policies might locate the hole, they often fail at the critical insertion moment. Another common failure case for vision-only policy occurs during the grasping phase, where an improper grasp position can lead to unintended collisions with the puzzle box during movement. GelFusion, however, uses tactile cues to guide the peg accurately, significantly improving success rates in these challenging. For tasks like picking up fragile objects such as potato chips, vision-only policy often fail, not by crushing the chips, but by applying too little force due to premature grasp timing decisions based on similar visual inputs. GelFusion, with its tactile feedback, ensures accurate force control, enabling successful and delicate handling. In conclusion, GelFusion combines visual and tactile feedback to address the challenges of contact-rich tasks where vision alone faces limitations. Its design improves performance in scenarios like precise alignments and delicate handling. Thank you for watching.